Hey everyone, today I want to introduce the basics of CMOS design. So, what is CMOS? CMOS actually stands for complementary metal oxide silicon. And really, the only thing that we're going to truly care about in this class is the C part of it. The MOS part of it is pretty easy. So, if you look at the a typical MOSFET, you'll get one of two types. You'll get a P-type transistor, which just will denote by this, and we'll get an N-type transistor. Actually, let me go ahead and write P-type, and then we'll get our N-type. N-type. E. So P-type, the way that I always remember it is P has a circle, and that has a circle. And P-type are usually going to be connected to a positive half of the of our circuit, which I'll explain a little bit more of that later. So I'm just going to go ahead and write this up here. So VCC, and then this will be down here to NMOS, and then this one is usually going to be the N-type is going to be on the lower half of the CMOS design, and we'll say that this is going to be going up to PMOS, and it'll be usually connected to ground. And then this right here, I'll call the gate on both of them. The gate is going to tell us whether this transistor is going to be on or off. In other words, whether it's going to let a signal go from here down to here, or from here up to here. Well, really, it's just letting the signals pass between this wire. You can think of it almost as a wire between, and this is just a switch. So, for P-type, P-type is going to be on when gate is set to 0. In other words, when we put a 0 for the input, this thing will be, it'll let a signal pass. Otherwise, if it's a 1, nothing will pass. Basically, the circuit is open. So, in an N-type transistor, the opposite is true. So, G is going to equal to 1 for it to pass a signal. So, let's do some basic designs. And I'll start with the most simplified form of the most simple transistor that we can get. So, and that is the NOT gate. We already know that NOT is like if we have A and then I have an output, then 0 goes to 1 and 1 goes to 0. Simple enough. So how do we design our CMOS logic? Well, I'm going to show you guys a little trick. We only ever, the C part of this that I was talking about before means that we only actually have to look at half of the circuit, or derive half of the circuit. The other half just comes as a byproduct. So in this case, I want to design the negative half. So let's see what A is. So Y here is equal to not A. Okay, so let's just look at this NOT and see the parts here. So I'm going to circle everything that has a 0 in it. And then I'm going to connect that to ground. So, and we'll do that with our, you guessed it, the NMOS transistor. And then I'm going to go ahead up here and create a PMOS transistor. Since there's really nothing else that we can do to make this circuit like more complicated, let's just connect the inputs. So here's our A, and then this will be VCC, and this will be Y. Now if you follow this circuit, if A is 1, this circuit is on, so ground comes, it pulls it up from ground. In other words, Y becomes 0. Y equals 0 if A equals to 1. Likewise, if here let me change color real fast. If A equals to 0, then this is pulled down from VCC, so Y equals to 1. Simple enough. Okay, so let's go on to our next gate. Let's do a NAND gate. Here, let me change back my colors. So I'm going to do a NAND gate, and this will be it'll be a lot clearer for showing the complementary part in this. Over here, we notice that we just have one NMOS to one PMOS. Well, we're always gonna, for each NMOS, we're always gonna have one PMOS, and the complementary part basically says if we solve for this half, then this half up here is just going to be the complement of it, of whatever's down here. So what is NAND? NAND, of course, if we have our A, B, and then output Y. Actually, let me go ahead and instead of writing Y here, I'm going to go ahead and write A, B, not, and so it'll be the NAND. So we got 0, 1, 0, 1, 0, 0, 1, 1. Okay, so for NAND gate, it's basically not AND. So we get a 0, 1, 1, and 1. So, like before, let's go ahead and circle our zeros. I'm just going to do it in a highlight this time. So we've got our 0 there. And how can we get this output of 0? Well, if NMOS is what's connected to our ground, then let's just link these two things together serially. So that's what we'll do. I'll have one transistor, second transistor, and then ground. So this will be our, it doesn't really matter what order, I'll just put a B there, I'll put an A here, and then we'll go up to something. This will be our NMOS circuit up here, and of course we'll have our output A bar B. But what goes up here? Well, it's just going to be the complement of whatever's down here. Since these two things are serial, what's up here should be in parallel. So it'll look something like this. Let me, sorry for one sec, my tablet is being a little bit weird. I'll put a B there, and then this one is going to be A. And then they just get both connected to VCC. So now let's go ahead and verify what we did. So if A and B are both 1, this will be true. So we get a path to ground pulling up. I'm going to change colors. Erase that. No! No! No, no, don't delete that. Okay, there we go. Saved it. So if A and B are both equal to 1, then we have a path up from ground. Otherwise, if A is 0 or B is 0, we get a path down from VCC. So if A equals 0 or B equals 0, then VCC. Otherwise, if A and B, then 0. And that's basically the logic that we've said over here. We notice that if we get any sort of 0, then the output is going to be a 1. Okay, so let's do one more final basic gate, and that is our NOR gate. So, NOR, of course, we have A, B, and then A or B, not for NOR. 0, 0, or sorry, 0, 1, 0, 1, 0, 0, 1, 1. And then what is a NOR? Anything that is going to have a 1 here is going to be a 0. So 0, 0, 0, and then 1. It's the opposite of NOR. So let's go ahead and create this circuit really fast. Notice how over here, all of these things are 0. The same sort of thing, reason that all of these things up here are 1. So we can actually derive the circuit in two ways. We could do what we were doing before and say, let's do the 0 half of it. Or, since I'm lazy, I could just look at this part. And that's what I'm going to do. So since we want two things that its inputs are 0 and we get an output of 1, well, we can just use our PMOS. So let's do that. We've got our VCC, 1, 2, just doing them in serial, so A and B. Well, technically it's going to be A naught and B naught. And again, the order of these two transistors doesn't really matter. A, B, and then now we have our A or B naught, and we just need to solve for the NMOS spot. Well, since these two things are in serial, whatever's down here should be in parallel for its group. So we've got, I'm just going to go ahead and draw a line like that to make it easier. Oh, I shouldn't have done it that way. Don't. And done. Here we go. So B, B, and then A. Man, my tablet is not working today. Sorry about that. So, now we can just go ahead and verify again. If we get a single input as a 1, then this is going to be pulled up from ground. Otherwise, if we get both inputs as a zero, we'll get pulled down from VCC. And that's really all there is to it. The point of CMOS design is that complementary. That is the biggest part of CMOS. The C equals complementary. I probably misspelled that. Ignore it. Yeah, that should be an E, shouldn't it? Complementary. It doesn't really matter. Anyways, the complementary means that whatever's down here, its complement will be up here. And whatever's up here, its complement will be down here. So, it should always, like, when you check your circuits and you want to make sure that it's actually a CMOS design, you really only have to check half of it. Like when you're transforming from the truth table over to the circuit, or the circuit to the truth table, you just do half. Then the other half should just follow. So in this case, I could solve for 1 because it's easier, and then everything else is just going to be zeros. Okay, that's really all I wanted to cover for today. I will post another video with some more examples soon.